Ripple tank is an experimental apparatus that is used for studying the characteristics of a wave. It is made up of a shallow transparent tray of water, as you can see here, a point light source, white screen displaying a bright and dark pattern of the crest and troughs, respectively. This is it. Horizontal metal strip for straight parallel waves, vertical ball-ended rod for circular waves, so it could be used. So either the horizontal metal strip for straight parallel waves is used, or the vertical ball-ended rod for circular waves, so it could be converted here. This all depends on the objective of usage. Okay, so this is the straight one, horizontal one, or it could be turned around in order to use the balls, so that circular waves or ripples are formed in the water. And we have the rheostat, which is a very important part of the electric circuit of this apparatus. It is used to control the speed of vibration of the rod and thus its frequency. So we have this strip vibrates up and down. So it could be vibrating at a frequency of 3 hertz, 4 hertz, 5 hertz, 6 hertz. This all could be adjusted. Okay, and what really controls it is the rheostat of the electric circuit. And finally, we have the stroboscope. It allows the viewer to observe a stationary image of the continuous pulses of the wave. So what is a stroboscope? Briefly, a stroboscope is a device that allows us to take a stationary image of a moving object. How is that? This is by like as if imagine you have some person moving around a certain loop, and he starts from initial position A, for example. So he goes all around from A until he comes back to A. So suppose a viewer is looking at this man. If he opens his eyes at the instant he starts moving from A, then close them as the man goes around. Then open the eyes again when the man reaches point A again. So the man will appear to be stationary or at rest with respect to the viewer because he did not change his position. So the idea of the stroboscope is just the same. It allows us to have a stationary image of an object that is moving or something that is in motion, so that we can study the characteristics here. And in this case, we get a stationary image of the wave. You can check out more videos on YouTube about stroboscopes and about ripple tanks. Now, for the exercise, we have that in question 6, in a ripple tank filled with water, the lab instructor placed a rectangular glass plate under the surface of water. In a ripple tank filled with water, the lab instructor placed a rectangular plate under the surface of water. So again, if we go back to the image of the ripple tank, suppose a piece of glass is put here on the tray that is filled with water. The students observed two regions in water and at different depths. And this is expected because as we put a level here or a layer here on the tray, this region here in which the glass is placed has lower depth than the other part that does not or that is not covered with a glass plate. The observed waves or periodic vibrator, which is the strip here, the horizontal strip that we saw, sends 300 vibrations per minute across the water tank. So the observed waves in the tank are represented in the adjacent figure. The distance separating the 2 points A and D is 9 cm, and that separating E and J is 10 cm, and the above figure is not drawn to scale. So regardless of the number of boxes, just consider the given distances. And here I would like to mention that the image here, this image, deep region, shallow region, this image is a side view of the wave. This is how we see it from the side view. However, if we look at the waves from the top, we can see that they look like plane waves. Okay, and all these ones are crests that are joined together. If we join the crests by a certain line, we obtain this line here. So this is a side view, this is a top view of the wave. So what's the question now? Define the wavelength of a wave and determine its value in each region. So the wavelength of a wave is the distance covered by the wave during one cycle. Now we are given that the distance AD is 9 cm. Let's check this AD distance includes how many wavelengths. So the wavelength is the distance between two consecutive requests. In this case, it includes 1, 2, and 3 wavelengths. So we can express it as such. We can say that 9 centimeter is equal to 3 lambda. So solving for lambda, divide both sides by 3, we get that lambda is equal to 3 centimeter. Similarly, for the shallow region, we have to count the number of wavelengths included within this distance. So it is 1, 2, 3, 4, 5 lambdas. So we have 10 centimeter equal 5 lambdas. Then lambda equal 10 over 5, so it's equal to 2 centimeter. Now, by referring to the given, calculate the frequency of the vibratory motion of the horizontal rod. Deduce the frequency of the wave. So we are given, what are we given about the vibratory source? We were given this here, that the vibratory source vibrates or performs 300 vibrations per minute. So we're given the number of vibrations n and the duration delta t. That's why we can apply the formula F equals a vibration equals n over delta t, which is 300 over 1 minute. But here please make sure that you convert from minute to seconds in order to obtain the frequency in the SI unit. So 300 vibrations over 60 seconds, 1 minute is equivalent to 60 seconds. 5 vibrations per second, do not leave it as such. You have to show me that vibration per second is actually the hertz, where hertz is in capital H and small z. Now deduce the frequency of the wave. We all know that the source or the cause of a wave is a vibratory source. And we know that a vibration or vibratory motion is characterized by its frequency, and a wave is also characterized by its frequency. The frequency for vibratory motion is how many cycles or how many oscillations is performed per second, and the frequency of a wave is how many cycles are performed per second. So for sure the cause and the effect must have the same frequency. That's why this is a rule, keep it in mind. F vibration, F of the vibratory source is equal to the frequency of the wave, which is 5 Hz in this case. Finally, deduce the period of the wave. This means that you have to make use of the previous results. So having the frequency and we need the period directly, you have to apply the formula T equals 1 over F. Here we are considering the wave, the period of the wave and the frequency of the wave. So 1 over 5 Hz is equal to 0.2 seconds. Calculate the speed of the wave in each region, compare the obtained results, then draw out a conclusion. So calculate the speed of the wave in each region. This means that maybe the speed is changed. We can expect this because we know that the same wave keeps the same frequency as it propagates from one medium to another. But since here the wavelength changed of the same wave, this means that this is due to the change of the speed. So now let's check it mathematically if this agrees with our acquired knowledge or not. We have to apply the formula V equal lambda times F, and the frequency of the wave remains the same. So for the deep region, it is equal to 3 centimeter times 5 Hz. Here, please make sure that you convert from centimeter to the SI unit, which is the meter, by dividing by 100. So we get 0.03 meter times 5 Hz equals 0.15 meter per second. For the shallow region, 2 centimeter times 5 Hz equals 0.02 meter times 5 equals 0.1 meter per second. So what can we conclude concerning the speed? The speed of a wave changes as it propagates from one medium to another because 0.15 is different from 0.1. Now you have this as a homework for next time. Have a good day.